Hello everyone. Today I'll be talking about my finite element analysis project, which is based on Buttress roots. So the image in front of your screen right now is what Buttress roots are. Buttress roots are basically roots that are large flared roots which extend from the base of the trunk, often forming like plank-like structures, and they basically radiate outwards from the tree. These roots are typically prominent in tropical rainforest and are also commonly observed in large hardwood species. The roots themselves generally rise about several meters above the ground. Here is a context image for how big the roots actually are. This is a human in front of the buttress roots, which gives you the context of how big the roots are. The development of buttress roots is fascinating because of the adaptation to the specific environmental changes that the trees are exposed to in tropical rainforests. So, so to start with the finite element analysis of buttress roots under wind loading condition, the first thing that we need to understand is how the normal large hardwood trunks perform under wind loading conditions in the absence of these buttress roots. So the first thing is to model the trunk. For this, I selected the 3D wire uh, section for the part which is the trunk, and the length was about 10 meters. For the radius of the trunk, I considered it as 0.5 meters, so which gives you this kind of part. Now, using this, we move on to the property module, wherein the material properties that I selected were for a hardwood species of the tropical rainforest, and these are the properties. The first thing is the density, which is 0.8 gram per centimeters cube. I converted it into 800 kilogram per meter cube. Then we have the elasticity. So the major difference between normal woods and these woods that are present in the tropical rainforest is the Young's modulus. So one of the things that evolution has uh, incorporated into these particular large hardwood species is they have become stiffer and stiffer over time. These large hardwood species have a Young's modulus of 22,160 megapascals, which is very interesting. Along with that, a Poisson's ratio was 0.35 that I considered, which is also common among large hardwood species. Using this, then I assign the materials to the beam section. Then we move on to the assembly. The assembly is basically just the trunk because we are trying to model just the trunk in this, in the absence of the buttress roots. So moving on to the step, a static step was created, which can be seen right here. Then we move on to interactions. There aren't any interactions which we'll be dealing with in the next section where we'll be modeling the trunk along with the roots. Now, for the loading, since in the tropical rainforest, it is dense and there are many trees, not all of the trunk is exposed to the wind loading. In this case, I considered the trunk to be exposed to wind loading to be the top 5 meters. So, a wind load of 330.75 Newton meters was applied. In this case, I calculated the wind load using drag coefficients, then the air density, wind velocity, and the diameter of the trunk, which can be found in the report. Uh, Using this, I considered a wind velocity of extreme winds, which is generally the case during rainy seasons in the tropical rainforest, and it was about 30 meters per second. So, using this, I applied a line load to the top 5 meters of the trunk, and I also anchored the base of the trunks to uh, allow for bending in the trunk. So using this, then I meshed the beam with the P33 elements, which can be seen right here. So these elements provide a two-node cubic beam in space, and this allowed for me to determine the stresses, which can be seen in the next one. So if we go to the job and results, this is what the stresses look like. Uh, Make sure that you have disabled the make sure that you have disabled the uh, averaging, because it might provide you intermediate values. So in this case, the stress that is visible at the base of the trunk is about -126,337, which is a huge stress when exposed to wind loading conditions. So after we determined the stress in trunk without the buttress root, now we move forward to determining the stress with buttress roots. So in this case, I model the buttress roots in a triangular cross section to represent the structure of the buttress root. This directly doesn't imply that all of the buttress roots are in triangular cross section. Most of them are, so I chose the triangular cross section for that. This cross section has been modeled in shell planar, 3D shell planar, and in that we have a 2 meters length from the base of the trunk and 2 meters in height from the ground. Then we have the trunk, which was basically modeled similar to the part with the trunk without the roots, 10 meters in height and similar uh, radius of 0.5 meters. Then moving forward with that, we go to the property section. Again, similar properties to that of the trunk without the roots was applied here. All of this was applied to the trunk as well as the roots. For the roots, the section was considered to be uh, shell homogeneous, and for the trunk, it was beam constant. Then moving forward with that into the assembly. So this is the part where it becomes a little chaotic. So the way I incorporated all the roots into the trunks is to first in the assembly you have to uh, bring in a single root. So what I did was in the assembly you have to do trunk and then offset it from a distance and roots. That's how your assembly should look like. So once you have incorporated the trunk and the root, next thing is to basically create a pattern, a circular pattern. So I used the radial pattern tool. Uh, in this, I selected the root as the instance and then selected the trunk as the axis, and I rotated it 360, creating 8 instances, which can be seen in the assembly right here. So these are all the roots. Then I manually selected. Uh, then I manually selected this part of the surface of the root, and I translated it to the trunk to create like an attachment. Uh, this was further tied together to the trunk using the interaction module. Uh, Again in step, similar static general, and then in the interaction, here's where things get interesting. Instead of using the coupling, I considered a tie constraint to basically transfer all the displacement from the trunk to the roots. Uh, in this, you can see I selected the shells of these roots, like the surface of these roots, and tied it to the main surface of the trunk to ensure that the displacement gets transferred. Now, moving on to the load section, similar to the trunk without the roots, I again applied a wind load, a uniform load of 330.75 Newton meters. And in order to replicate that the roots are anchored, I basically uh, constrained all the displacement and the rotation at the base of the roots. Now, Moving on to the mesh. The beam, the trunk, basically the beam was modeled using the V33 element, a two-node cubic element, which I have shown in the previous one. And the for the roots, the roots I used quad free element shape, uh, and I used quadratic. So the reason I used this because I wanted maximum bending stress, and I also wanted to understand whether or not the shell elements support bending. So this proved my point, right? That they do. Using a quadratic provides you a more convergent result. If you want to use linear, you can, but then the convergence won't be that good. That's why I used a quadratic element, a quadrilateral element, and a quadratic geometric order, which gave me an S8R, an 8-node doubly curved thick shell. Using this, I meshed the triangle. I made sure that most of the nodes are saturated at the this particular point because that's where the maximum stress and buttress roots will occur under wind loading conditions. For that, uh, I selected local sheets, then I used single biasing, and you can see clearly that I have saturated all the nodes right here. So using this, then we move on to the job. Basically, it is similar to uh, using like a static simulation. So I did that, and once it runs, I can show you the results. So first thing first, it is clear that my the roots should basically dissipate most of the stress and reduce the stress on the trunk. So using this, we can now go to, yeah. So using this, we can see that the node at the base of the trunk provides you a stress of 65456.5, which is about 48.19% decrease from the stress with in the trunk without the roots. This clearly indicates that buttress roots dissipate stress under wind loading condition, which was uh, further uh, mentioned in most of the articles. So moving forward with the earthquake simulation, this was something that was kind of interesting to simulate. For this, I used the trunk with the roots simulation, and the only thing that I switched was the number of steps. So in this, I incorporated uh, another step, which was a dynamic step. You can see right here. And in this, the loads are kind of different. So if we go to the loads, in this, I only fixed the ends of the roots because most of the ground would be moving, only the ends would be held stiffen. And there won't be any load as such, only there's a displacement at the base of the trunk to simulate the earthquake movement. So for this, in order to create like a left and right movement, I went to plugins, tools, then in this I went to amplitude plotter. So if you want to, you could manually do it, like incorporate all the values x direction, y direction, and get a plot similar to this. But what I would suggest is to create a script which basically does that for you. So for this, I used a Python script, which I then implemented into Abacus. What this script does for you is it creates a amplitude of the earthquake, and you then don't have to manually put in all the values. So first thing, we import all the abacus constraints, then we import a visualization, and we import numpy. Then I basically used a CSV file, which was basically an example earthquake CSV file, which included all the displacement and the time values. Then I uh, skipped the header in, took in all the data values. Then I bifurcated it into time and uh, displacement. My bad, that's displacement. Yeah. and then I converted into tuples, then a model name and example and everything. And then you basically select the script. So you go to run, then uh, yeah, you basically select the script, and once you hit OK, in the plugins, it should appear right here. So once you select that, now the next step is to uh, apply that to the boundary conditions. Uh, in this case, that's my boundary conditions, which basically is the displacement. And in this, it would be on default by default on the instantaneous. You have to select the amplitude and hit OK. So once you do that, and similar mesh to that of the trunk with the roots, and then you hit submit. It should run for a while, and then it'll give you the results of the simulation. So, so once you do that, this is the simulation that you will get. See, it is clear that the trunk is moving from left to right, and the roots are kind of opposing that. But the major thing is to set the history field outputs. So in this, I created a history field output. In that, I selected stress, and I selected the S11, which is the stress in X direction, because that's where the force I have applied. And similar to that, in the field outputs, I also did the same thing, stresses, misses stresses. So from this, you can clearly see the graph plots. Oh, sorry. Yeah, so it will give you a plot similar to this, which increases till one and then becomes constant, which should be the case with the buttress roots since they support uh, the stability of the trunk, and once it reaches to a certain stress, it should then become constant because that's the anchorage strength property of the buttress roots, which we are trying to simulate here. So using this, I then simulated basically a dynamic condition in which the buttress roots uh, hold the trunk stable. In the absence of this particular property, the anchorage strength, which is absent in trees that are in low-lying areas and have a deeper root structure and nutrient-rich soil, the tree would fail terribly. It would just break at the base of the trunk and then fall over. But in case of the buttress root, due to this anchorage strength property, there are less tears or mechanical failures at the base of the roots since the buttress roots are effective in distributing the stress all over the roots and on the trunk, which is essential for the habitat that these roots are present, which is tropical rainforest, which experiences extreme winds and such seismic conditions. Thank you for joining this tutorial. Uh, this is one of the uh, analysis that inspired me a lot to look into tree structures and biomechanics in particular. Uh, this basically inspires most of the engineering solutions out there, which can be seen in the University of Colorado Boulder, where there are various buttress root inspired arches and supports. So, thank you.